In this video, I will introduce you to the use of source superposition to find circuit outputs due to multiple independent sources. So to do this, we have to have a linear circuit. So a circuit's linear if its output, some current or voltage, is directly proportional to the excitation at the input. We're interested in actually excitation from multiple inputs. Circuits with ideal passive elements, so we're talking ideal resistors, ideal capacitors, ideal inductors, these all satisfy linearity. So if we have a linear circuit, then it's going to satisfy the superposition principle. And that is to say that if a circuit contains multiple independent sources, the voltage or current responses of any element is going to be equal to the superposition of the individual responses due to each independent source acting alone. So you think about it, say we have like 5 independent sources and you want the current across some resistor X, okay? Well, what you do is you turn off all, like 4 of them except one, and you get the current at that resistor, through that resistor, due to the one source, and then you turn the other, everything off again except another source, get the current through the resistor, and then you repeat for all 5 of the independent sources one at a time, and then you just sum up the current through that resistor in all the different cases, and then that's your superposition solution. You can do this with voltages too. So we're going to do this in an example, but we're going to start with this circuit and we're going to use nodal analysis because that's going to be our reference and we'll say that we got it right. So let's just start nodal analysis. We get to pick a ground. So we'll pick this bottom node. We notice that there's a top node here and another node. There's one more node here and we actually don't really care about it because for nodal analysis, you want the current flowing through, well, we already know the current flowing through that node, but what we're really interested in here is the top node. Let me show you why. It's because we're calling this ground, so that's clearly 0. If that's 0, well, then this then is 8 volts. We already know that. The only unknown is this node, which, because it's V volts higher than ground, we'll just say that's V. That's the very V that we're looking for. So we know that it's 1 amp flowing through here, and so we don't need this nodal voltage at all, and we can just write a Kcl equation for our node of interest right there. So I used currents leaving and I summed them to 0. I could have used currents entering. The whole point is just be consistent. Now we have one equation, one unknown, we can solve it. So now we know this is 4 volts, and now we can easily find the current I. That's 8 minus 4 over 4. And then we can also double check. This current going down like this, that has to sum up to the 1 amp and the 1 amp coming in from the left and the right. So you can see here this has to be 2 amps. And that makes sense, right? Because 2 amps flowing through 2 ohms is 4 volts, and that's precisely the voltage drop across that resistor. So we should feel happy that we have an accurate and correct solution. Now we will do this using the superposition principle. We'll make note of our reference solution here. Additionally, let us write a procedure for the superposition technique here. So we want to turn all sources off except for the kth source. So every source that's not the kth source will do this. If a source that we want to turn off is a current source, then we replace it by an open circuit. So you can think of this as a current source of exactly 0 amps. If it's a voltage source, then we replace it by a short circuit. Right? Because a short circuit allows 0 voltage across it. So I wrote sideways, sorry about that. The next step is to draw the circuit with all the sources off. we solve for the output of interest. Finally, we solve for the total output. We'll point out that in number 2, this is the desired output due to the kth source. In part 3, we'll say this is due to all sources. All right, that's our procedure. Now let's apply it to this circuit. I've copied the circuit here. Let's focus on the voltage source. So I've made a table so we can track how all this goes. So with the voltage source only on and the current source off, well, that current source will be replaced by an open circuit. So let's draw the circuit again. I'm going to give the I and the V subscripts 1 here because this is our first case. In the first case, we see that no current flows through the resistor. That means that I1 is the same flowing through here. The 4 ohm and the 2 ohm are in series, if you recall the definition of series, so one node connecting 2 elements and no other current carrying connections. So that means that there's no current carrying connection here because of the I equals 0. So the 4 and the 2 are in series, so we can easily get I1. All right, so let's mark this down. So the voltage source gives us I1 is 4/3 amp. And we can get V1 using the voltage divider. That makes sense because if it's a 2 ohm resistor, the current through it gets multiplied by 2, which is 4/3 becomes 8/3. All right, so now we turn off the voltage source and we turn on the current source. So we'll put here current source only. Inserting the picture again, now we turn our voltage source into a short circuit. And what happens here? We have 1 amp and then it flows through the 4 and the 2 in parallel. So we can use current divider to get the current through each of those resistors. Keep in mind that we're using 1 amp of current that flows this way. So now we'll figure out how it divides into currents going this way and that way. We'll call them I1, I2. Better yet, I'll call them IA and IB, not to be confused with the I1 up above. So for IA, we can use current division. And so now we have IA equals 1/3 amp and IB equals 2/3 amp. That makes sense because the 1/3 and the 2/3 make the 1 amp coming in. So that tells us then that I2, let's put here I2, V2. Now let's write that up here. And now we can add these together. So 8/3 and 4/3 is 12/3, and that gives us 4 volts. Well, I1 is 4/3, I2 is -1/3, so the total there is 1 amp. So those are the total responses we calculated for these two current sources. We did them independently, we added them back together. And what I'll point out here is that our total response, 4 volts and 1 amp, is the same as what we did using nodal analysis. So I first analyzed the circuit using nodal analysis, and then I looked for both a current and a voltage, and I showed you how to use the superposition principle for 2 sources. Of course, you can do this for more than 2 sources. You just have to do them one at a time. And so I hope that is helpful to you. Remember to like the video, subscribe to the channel, share it. Thanks, and have a great day.